Hello and welcome back to Introductory Astronomy. In this picture right here, we see a galactic black hole. A network of radio telescopes has probed the core of the spiral galaxy NGC 4258, which is shown here in the light of mostly hydrogen emission. Within the innermost 0.2 parsecs, shown in the inset, observations of Doppler-shifted molecular clouds, designated by red, green, and blue dots, show that they obey Kepler's third law perfectly and have revealed a slightly warped disk of rotating gas, shown in the inset as an artist's conception. At the center of the disk presumably lurks a huge black hole. Careful observations of nearby normal and active galaxies reveal that the mass of the central black hole is well correlated with the mass of the galactic bulge. In this diagram, each point represents a different galaxy. The straight line is the best fit to the data, implying a black hole mass of 1/200th the mass of the bulge. Binary black holes. These, frame A optical image taken by Hubble and frame B extra image taken by Chandra, are images of the starburst galaxy NGC 6240. And as you can see, it shows two supermassive black holes, the blue-white objects near the center of the X-ray image, that are orbiting about 1 kiloparsec apart. According to theoretical estimates, they will merge in about 400 million years, releasing an intense burst of gravitational radiation in the process. The colors of the optical image are real. The false colors in the X-ray image indicate a range of energies in the X-ray band. Quasar-host galaxies. These long-exposure Hubble Space Telescope images of distant quasars clearly show the young host galaxies in which the quasars reside, lending strong support to the view that quasars represent an early, highly luminous phase of galactic evolution. The quasar at the top left is the best example, having the catalog name PG0052 plus 251 and residing roughly 700 megaparsecs from the Earth. Note that several of the quasars appear to be associated with interacting galaxies, consistent with current theories of galaxy evolution. The end of the quasar epoch seems to have been about 10 billion years ago. All the quasars we have seen are older than that. The black holes powering the quasars do not go away. It is believed that many, if not most, galaxies have a supermassive black hole at their centers. Let's take a look at galaxy evolution. Some possible evolutionary sequences for galaxies, beginning with galaxy mergers, leading to the highly luminous quasars, decreasing in violence through the radio and Cepheid galaxies, and ending with normal ellipticals and spirals. The central black holes that powered the early activity are still there at later times. They simply run out of fuel as time goes on. Here we have a 3D diagram of the Virgo supercluster. The elongated structure of the Virgo supercluster, which is located, at left center, is mapped relative to other neighboring galaxy superclusters within about 100 megaparsecs of the Milky Way. Individual galaxies are not shown. Rather, we have smooth contour plots outlining galaxy clusters, and each of them is named or numbered by its most prominent member. Here we have the first slice of a survey of the universe covering 1,732 galaxies out to an approximate distance of 200 megaparsecs, and it clearly shows that galaxies and clusters are not randomly distributed on large scales. Instead, they appear to have a filamentary structure surrounding vast, nearly empty voids. We assume that h0 is 70 kilometers per second per megaparsec. This slice covers 6 degrees of the sky in the direction out of the plane of the paper. Here we have a large-scale galaxy survey carried out at the Las Campanas Observatory in Chile, consisting of 23,697 galaxies within about 1,000 megaparsecs in two 80-degree by 4.5-degree wedges of the sky. Many voids and quote-unquote walls on scales of up to 100 to 200 megaparsec can be seen, but no larger structures are evident. Quasars are all very distant, and the light coming to us from them has probably gone through many interesting regions. We can learn about the intervening space by careful study of quasar spectra. Here we have a picture of what is called the Lyman-alpha forest spectra. When light from a distant quasar passes through a foreground cloud of atomic hydrogen, the absorption lines produced bear the cloud's redshift. The huge number of absorption lines in the spectrum of this quasar, which is called QS01422 plus 2309, are the ultraviolet Lyman-alpha lines from hundreds of clouds of foreground hydrogen gas, each redshifted by a slightly different amount, but less than the quasar itself. The peak at left marks the Lyman-alpha emission line from the quasar, emitted at 122 nanometers, but redshifted here to a wavelength of 564 nanometers in the visible range. Let's go back to slide 9 really quick and look at the Lyman-alpha forest in relation to the rest of the northern sky. The Lyman-alpha forest is represented by the thin blue arc in the figure here. This quote-unquote double quasar, designated AC114 and located about 2 billion parsecs away, is actually not two separate objects as originally thought. Instead, the two large blobs at upper left and lower right are images of the same object created by a gravitational lens. The lensing galaxy itself is probably not visible in this image. The two objects near the center of the frame are thought to be unrelated galaxies in a foreground cluster. So what could cause this scenario? What is called gravitational lensing. When light from a distant object passes close to a galaxy or a cluster of galaxies along our line of sight, the image of the background object, in this case a quasar, can sometimes be split into two or even more separate images, in this case image A and B. The foreground object is a gravitational lens. A very popular gravitational lensing effect is called the Einstein cross. If you take a look at frame A, in this case we have a multiple imaged quasar. In this Hubble view, spanning only a couple of arc seconds, 4 separate images of the same quasar have been produced by the galaxy at the center. In frame B, we have a simplified artist's conception of what might be occurring here, with Earth at right and the distant quasar at left. Here we have other examples of galaxy cluster lensing. In frame A, we have a spectacular example of gravitational lensing that shows more than 100 faint arcs from very distant galaxies. The wispy pattern spread across the foreground galaxy cluster, A2218, about 1 billion parsecs distant, resembles a spider's web, but it is really an illusion caused by A2218's gravitational field, which deflects the light from background galaxies and distorts their appearance. By measuring the extent of the distortion, astronomers can estimate the mass of the intervening cluster. Frame B, we have an approximately true color image of the galaxy cluster known only by its catalog name, 0024 plus 1654, residing some 1.5 billion parsecs away. The reddish-yellow blobs are mostly normal elliptical galaxy members of the cluster, concentrated toward the center of the image. The bluish loop-like features are images of a single background galaxy. Here we have a dark matter map. By measuring distortions in the images of background objects, astronomers can make maps of dark matter in the universe. These contours show the distribution of dark matter in and near a small galaxy cluster, derived by analyzing the images of background galaxies. And of course, clusters of galaxies must occasionally collide, as this one, having the innocuous catalog name 1E0657-56 and the nickname Bullet Cluster. This is a composite image of a region about 1 billion parsecs away, showing optical light from the galaxies themselves in white and hot X-ray emitting gas from the intracluster gas in red. By contrast, the blue color represents the inferred dark matter within the two large clusters that is distinctly displaced from their normal matter. Astronomers estimate that this might have been the most energetic collision in the universe since the Big Bang. I'd like to talk a little bit about the Sloan Digital Sky Survey. This survey of the sky is being done by a dedicated 2.5-meter telescope located in New Mexico. Its purpose is to measure hundreds of millions of celestial objects with 5 intensity points spanning the visible and near-infrared wavelengths. Approximately 1 million of these also have their redshifts measured, making possible very detailed redshift maps. If you would like to learn more about the SDSS survey, I have the link on the lower left there of the slide. You can collect data once you sign up and have your computer analyze it. That way you can contribute in the effort to map the sky. I also put a link to a short video that shows how the sky has been mapped using the SDSS data collected thus far. So the summary of Chapter 25, we talked about the galaxy masses and how they can be determined by the rotation curves and the galaxy clusters. All measures show that a large amount of dark matter must exist. Large galaxies probably form from the merger of smaller ones, which is why collisions are very important. Merger of spiral galaxies probably results in an elliptical galaxy. Quasars, active galaxies, and normal galaxies may represent an evolutionary sequence. Galaxy clusters, just like star clusters, are gravitationally bound. And galaxy clusters themselves are gravitationally bound into what we call superclusters. The universe seems to have a structure up to about 200 megaparsecs. Beyond that, there doesn't seem to be any structure. Quasars can be used as probes of intervening space, especially if there is galactic lensing. study sections 25.4 and 25.5, and be able to summarize what is known about the large-scale distribution of galaxies in the universe. You should also be able to describe some techniques used by astronomers to probe the universe on very large scales.